lecture, we are going to discuss a very important concept called transfer learning. So first of all, we should know what is transfer learning, right? So let me take the pointer now. Okay. So let us try to understand what is transfer learning basically, right? Because before studying that, at least we should know what is transfer learning and what are the applications of transfer learning and why do we give more importance to transfer learning. So just think that let me start with a simple example, no, so that you can understand it in a better way. Say, for example, I'm a trainer over here. I have certain years of experience into this particular domain or the field, right? So I have this accumulated information in me, and what I'm trying to do is I'm trying to deliver the lecture to the students like you. Basically, I'm trying to give the overview of that topic, right? So basically what I'm trying to do now, I'm trying to transfer information, right? So basically I'm trying to transfer information to you, right? So now compare this with the neural network. A neural network is trained on particular data, then it gains some knowledge about the data, right? So a neural network will work on particular data. It will gain some knowledge about that data, right? So once it gains knowledge about the data, it will be compiling the weights of the network, and then these weights can be extracted and then transferred to any other neural network. So instead of training the other neural network from the scratch, what we do is we transfer the learned features from the first data, right? So this is what, very simple. Say, for example, a person who ride motorcycle, who can ride bike, can easily learn to ride the car, right? So basically what is happening here, he has knowledge in driving the motorbike or the motorcycle or the bike, and he is transferring that knowledge to learn the driving of a car. Very simple, right? So transfer learning is a machine learning method where a model developed for a task is reused as the starting point for a model on a second task. So what will happen over here is, it is not necessary to start from scratch into the second task. We use the learning that happened on the first task on the second task, right? So this is basically a very popular approach in deep learning, where we will be using the pre-trained models as the starting point on computer vision and NLP, right? So we will be using this resources to develop neural network models, right? So hope it is clear now, right? So what is meant by a pre-trained model? A pre-trained model means like that is basically used to solve some similar problem. So here we are not doing the second task from the scratch. What we are trying to do, instead of that, we are using this pre-trained model on the second problem that we are trying to solve over here. So here the another important point is that a pre-trained model may not be 100% accurate in the application, but still it will save a lot of efforts for us, right? So say we wish to find out the correct weights for the network by multiple forward and backward iterations, right? Let me tell this way. No, for example, we want to build a self-learning car. Okay, so we can spend a lot of years to build a image recognition algorithm from scratch, or even we can take an inception model, that is basically a pre-trained model from Google, which was built on ImageNet data to identify images on those pictures, right? So here the pre-trained model is not going to be 100% accurate in the application, but definitely it will save a lot of efforts, right? So this is what we have to understand, right? We cannot expect 100% accuracy in the sense it could be anything. Say, for example, I have tried on one model. So what I have done is I have taken 3 convolutional blocks. In each block, what I had was, this was the architecture I had. I had like 32 filters, of size 5 cross 5, right? And then activation function, what I had was ReLU, and then maximum pooling layer, right? Maximum pooling layer of size 4 cross 4, right? So here, the result that I got after the first convolutional block, I flattened it into the size of 256 and then passed it into single hidden layer with the 64 neurons, right? So the output of the hidden layer, then I passed with a dropout rate of 0.5, right? And then I found that accuracy and I compared it with the MLP output, and it also increased the time taken to run a single epoch by 21 seconds. So here previously I got around 6.8% accuracy, and then I found the accuracy to be increased to 17.6%. So even if I have predicted the class of every image in the training data set to be the majority class, we can perform better than MLP and CNN, right? So additionally, what I can also say that is more convolutional blocks increased my training time, right? So this made me to switch on to using pre-trained models, right? So then also I tried with the VGG16 model on the ImageNet data set, and also here what I did was I used the existing architecture, but changing the softmax layer with 1,000 outputs to 16 categories, which was suitable for the problem data set that I have taken, right? So here I could achieve around 70% accuracy. That is being better than MLP and CNN, right? So here I'm just sharing the experience what I have worked before. So here the biggest benefit of using VGG16 pre-trained model was almost negligible time to train the dense layer with greater accuracy, right? So I moved it forward with this approach of using the pre-trained model, and the next step was to fine-tune my VGG16 model to shoot this problem, right? So how can I use the pre-trained model, right? So what is our objective when we try to train a neural network? This would be the next question that comes to our mind, right? So we have to first identify the correct weights, okay, for the network. So how I can do that? By using the forward and backward iterations, right? So by using pre-trained models, what I will do now, we will directly use the weights and architecture obtained and apply on the problem statement. This is nothing but called as the transfer learning. So what I'm doing over here, I'm transferring the learning of the pre-trained model to our specified problem statement, right? So we have to be very much careful while choosing the pre-trained model, because if the problem statement we have at hand was completely different, then we may not be able to get the accurate result, right? So a model previously trained on speech recognition, and if I try to use it on object recognition, definitely it is not going to work well, right? So I hope I'm very clear about it, right? Nowadays we are having lot of pre-trained architectures, right? The image data set on various architectures we have worked, that is basically 1.2 images to create a generalized model. So basically we are training a model that can correctly classify the images into 1,000 separate object categories. So these 1,000 image categories represent the object classes that we come across in everyday life, right? So basically it will provide a strong ability, right? So now how can I pre-train, how can I fine tune my model, right? So the first point is about feature extraction. So I can use a pre-trained model as a feature extraction mechanism. So what I can do is I can remove the output layer, the one that gives the probabilities for being, say, the example that I have taken for 1,000 classes, and then I can use the entire network as a fixed feature extractor for the new data set. The second one is about use the architecture of the pre-trained model. So here what I can do is that we use the architecture of the model where we can initialize all the weights randomly and train the model, and then according to the data set that I want to handle. Then the third point is about training some layers while freezing others. Means like I can use another model to train partially, right? So what I can do is we can keep the weights of the initial layers of the model frozen while we retrain only the higher layers. So we can try and test how many layers to be frozen and how many to be trained. So I'll show you one diagram that will make you to clearly understand that basically. So let me write these scenarios over here. So let me write scenario 1. So what I try to say over here is size of the data set is small, but the data similarity is very high, right? The data similarity is very high, but size of data set is small. Okay, so size small, right? So similarity is right. So similarity is basically high over here. So what will happen here? The data similarity is high over here. So we do not need to retrain the model. What we have to do? Just we have to customize and modify the output layers according to our problem statement, right? So we should use the pre-trained model as a feature extractor. Suppose we desire to use models trained on ImageNet to identify the new set of images that are having cats or dogs, right? So here we have the images we need to identify would be similar to ImageNet. Then we just need two categories as the output, because here I'm saying like it could be cat or dog. So in this case, what we do, we just modify the output layer to two categories, because the ImageNet is having 1,000, right? So scenario 2, right? So here what I'm going to take now, size is small as well as data similarity is also small. So let me write that size as well as similarity, both are low over here. So here what we do, we can freeze the initial layers, that is the K layers of the pre-trained model, and then train the remaining like N minus K layers again, right? So the top layers would then be customized into the new data set. So the new data set has low similarity. It is significant to retrain and customize the higher layers according to the new data set. So the small size of the data set is compensated by the fact the initial layers are kept pre-trained, okay, and the weights of those layers are being frozen. Now let me write a third scenario. So what would be the third scenario? Yes, size is going to be large and similarity I'm going to take it as high. Okay, so in this case, what will happen? This is the ideal situation. Here, the pre-trained model should be more effective, right? So the best way to use the model is to retrain this architecture of the model and the initial weights of the model. So we can retrain the model using the weights as initialized in the pre-trained model, right? So let me write scenario 4 now. So here, what would be? Yes, you are right. So size is going to be large and the similarity is going to be low. So here what will happen? We have a large data set, but so that our neural network training could be more effective, right? But since the data we have is very different as compared to the data used for training or pre-trained model, the predictions made using pre-trained model should not be very effective. So it is best to train the neural network from scratch, right? Fine. So it is clear, I guess, right? Fine. So basically, it is very simple to understand the transfer learning. If one person know how to ride the motorbike, he will learn easily how to ride a car. If someone know how to play classic piano, he will learn how to play jazz piano. If somebody is good at mathematics and statistics, definitely he can learn machine learning very well, right? So this is what the transfer learning basically means, right? We should understand the basic difference between the traditional machine learning as well as the transfer learning, right? Basically, this first thing what we have to remember is transfer learning is not a new concept. It is not very specific to deep learning, but basically there is a difference between no traditional approach of machine learning as well as this one, right? So traditional learning is isolated and it can occur based upon the specific task or the data set and training separate isolated models on them. So no knowledge is retained which can be transferred from one model to another model. But in transfer learning, we can leverage knowledge obtained from one model that can be transferred to another model, and even it can tackle problems having less data for the new task, right? Say, for example, we are trying to identify the objects in images within a restaurant, right? So let's mark this task in the defined scope as T1, and for given a task, given the data set for this task, we train a model and tune it to perform well on unseen data points from the same domain, right? So the traditional supervised machine learning algorithms break down. We do not have sufficient training examples for the required task, right? So now we must detect objects from images in a park or a cafe. Let it be T2, right? So ideally, we should be able to apply the model trained on T1, but in reality, we face performance degradation and models that do generalization well, that do not generalization well, right? So this happens for many reasons. So we can liberally and collectively term as models biased towards training data and domain, right? So transfer learning should enable us to utilize knowledge from previously learned tasks and apply to newer or the related ones. So if we have significantly more data for task T1, we may utilize its learning and generalize this knowledge for task T2, right? And here we can have less data also, right? In the case of problems in the computer vision domain, low features such as edges, shades, corners, and intensity can be shared across the task, and whatever could be, this is possible, right? And also here we should also know in transfer learning that what we are transferring. So basically what to transfer, we should also know when to transfer. We should also know how to transfer. So let us understand that, like what to transfer in the sense, this is the first and the most important step in the whole process. We are trying to get the answers about which part of the knowledge we can transfer from the source to the target to improve the performance of the target task. When trying to answer this question, we try to identify which portion of knowledge is so specific and what is common between source and the target, right? So when to transfer, here there can be scenarios where transferring knowledge for the sake of it may make matters worse than improving anything. So we would be aiming at utilizing transfer learning to improve target task performance results and not degrade them. So we need to be careful about when to transfer and when not to transfer, right? So how to transfer? Once what and when have been answered, we can proceed towards identifying ways of actually transferring the knowledge across domains, right? So this involves changes to existing algorithms and different techniques which we will try to understand over here, right? So here let us discuss about the transfer learning strategies. What are the different strategies? You can see that like I have shown inductive transfer learning, right? Here what will happen is, like here the source and the target domains are the same, yet the source and target tasks are different from each other. So the algorithms try to utilize the inductive biases of the source domain to help improve the target task. So depending upon whether the source and domain contains labeled data or not, this can be further divided into two subcategories similar to multitask learning and self-taught learning respectively, right? So the next one is unsupervised transfer learning. So here this setting is almost similar to inductive transfer learning, but this will be focusing on unsupervised task in the target domain, right? So target is unsupervised, right? Fine. So the source and target are again similar over here, but the tasks are different, right? So in this scenario, labeled data is unavailable in either of the domains. So there is no labeled data over here, right? The next one is about transductive transfer learning. So here there are similarities between source and target task, but the domains are being different. So here the domains are being different, right? You can see that, right? So here the domains are being different, right? So what I can say is, like, here the source domain has a lot of labeled data, while the target domain has none. So this can be further divided into categories, either the feature spaces are different or the marginal probabilities, right? So the three transfer categories discussed here, where transfer learning can be applied, and this can be studied in detail. So you can see over here, right? Fine. You can see here transfer learning, inductive transfer learning, transductive transfer learning, unsupervised transfer learning, right? So now what you can see is about instance transfer. So here reusing knowledge from the source domain to the target task is used, is called as an no, is called as an ideal scenario. In most of the cases, the source domain data cannot be used directly. So what we do is, from the source domain, that can be reused along with the target data to improve the result. Okay. Feature representation transfer. The second one could be about feature representation transfer. Here we try to minimize the domain divergence and reduce the error rate by identifying the good feature representation. The third one could be about parameter transfer, right? So here it works on the assumption the models or later task share some parameters of prior distribution of hyperparameters. Next one could be relational knowledge transfer, right? Relational knowledge transfer in the sense, like, here it attempts to handle non-IID data, the data is independent and identically distributed, right? Fine. So basically what we have to understand over here is deep learning models are representative of inductive learning, right? So the objective is here to infer a mapping from a set of training examples. So in case if we are doing the task of classification, the model learns in case if we are doing classification, right? What will happen over here? The model learns mapping between input features and class labels, right? Input features and class labels, right? So in order to for such a learner to generalize well on unseen data, its algorithm works with a set of assumptions related to distribution of the training data, right? So these set of assumptions are known as inductive bias, right? So the inductive bias can be characterized by multiple factors such as hypothesis space. It restricts to and the search process through the hypothesis space. Okay. So the next one is about inductive transfer technique. Okay. So when you say inductive transfer technique, it utilizes the inductive biases of the source task to assess the target task, right? So it can be done in many ways. Now also we will discuss about the concept of one-shot learning, right? So what is meant by one-shot learning, right? Why do we one-shot learning? Also, we will study about multitask learning, and also we will study about zero-shot learning. Okay. So what is meant by multitask learning? Here it is slightly different flavor of transfer learning. So here what happens is several tasks are learned simultaneously without distinction between source and target. So the learner receives information about the multiple tasks at once, then as compared to the transfer learning, where the learner initially has no idea about the target task, right? So this is what being shown over here. Task T1, task T2, task T3. This is what the multitask learner, right? So in case if you take one shot learning, how that works is like a one shot learning. Here actually what happens is say let me start with a simple example. A child is shown what an apple looks like, right? They can easily identify different variety of apple, right? So this is not the case with the ML and deep learning algorithm. So one shot learning is a variant of transfer learning where we try to infer the required output based on just one or a few training example. So this is helpful in real world scenario where it is not possible to have labeled data for every possible class, right? So the next one is about zero shot learning, right? Right. So zero shot learning, right? So this is another variant of transfer learning here, which relies on no labeled examples to learn a task. But this looks like unbelievable when learning using examples is what most supervised learning algorithms are about. Zero data learning or zero shot learning methods make clever adjustment during the training stage itself to exploit additional information to understand unseen data, right? So now let us try to understand what are the applications of transfer learning. So when you take application in NLP, textual data basically presents all sorts of challenges when it comes to ML and deep learning, right? They are usually transformed or vectorized using different techniques. So the embeddings like word to vec, fast text have been prepared using different training data sets. So they are utilized in different tasks like sentiment analysis, document classification, by transferring the knowledge from source task, right? Beside all of this, new models like nowadays BERT, these are all also presenting possibilities for the future. Then the transfer learning for audio and speech. So similar to NLP and computer vision, deep learning is also has based on audio data, say automatic speech recognition models that are developed for English that have used to improve speech recognition performance, right? Say for example, an automated speech identification is another example where transfer learning has greatly helped. The next one is for computer vision. Here the deep learning has quite successfully utilized for computer vision tasks like it could be like object recognition or using CNN architectures, right? There are a lot of findings over here using the models like VGG, AlexNet, Inception model, right? Inception model, right? That are different. What these models are trained, right? So these are basically very important. And there are being several case studies like image classification with the data availability constrained, right? So you can, if you get time for that, just you can go through some case studies related to this so that you can get a clear knowledge about this transfer learning. Hope this session made you to clearly understand what is transfer learning and the applications of transfer learning and how the pre-trained models basically work, right? Thank you.